that's my talk. I first got to know Zhang in the early 1990s. I was like Doug Scalapino said last night, I was very confused that this guy who was obviously so brilliant and knew so much more about physics than me was actually interested in talking to me. And I'm not an organized person, as I've learned, unlike Xu Chang, and so I don't have any photos, but I do have two memories that I'd like to briefly share. Two memories, both of rainy nights, and that illustrate some of the breadth of Shoucheng that we've heard a lot about in the last couple of days. First night was a rainy night in Beijing sometime in the early 1990s. I don't remember exactly when. And Shoucheng took myself and my wife out to visit some local artists. And I purchased some art that night. I probably couldn't afford to do it now. And but I've been looking at that art with more deeper feelings since we all heard of the untimely demise of Shoucheng last fall. And another rainy night I remember, that you may remember, Lawrence, is a drive from Würzburg to Dresden. It was also a rainy night. Werner Henke was at the wheel. Lawrence was in the passenger seat. And I spent this entire drive discussing real-world magnetoelectric properties of topological insulators with Shoucheng, a topic that actually still interests me. These are, I think, some of the very, very best memories, both of them, of my entire scientific career, and I think that we all recognize how lucky we are to be part of this world. So I'm going to talk about a topic I've been working on recently. It's a topic in bilayer two-dimensional electron systems. The way I think about it, many aspects of the way I think about it are based on things that I learned from Shoucheng a long time ago. This session is on Spintronics. I was supposed to talk about something related to this cartoon. What this cartoon is trying to illustrate is for the Rashba model that Joe was talking about earlier, trying to illustrate states as a function of momentum, and trying to illustrate that those states are altered by an electric field because the electric field remixes the bands. And so this was an early attempt to try and generalize what we learned about the geometric approach to the quantum Hall effect to systems without broken time reversal symmetry, because the change in the states makes a change of velocity, which is related to Berry curvature, and this is actually a way of thinking about the quantum anomalous Hall effect that we learned about from David Thales and Duncan Haldane. And in the case where you don't have time reversal, the total current induced by this effect is zero, of course, but there is a spin current. And so this spin current represented by this cartoon for the Rashba model is related to the very large spin orbit torques that Stuart was talking about in the last talk. And actually, I happen to know, like Joe, that this is one of my most cited papers. And the reason it's cited is, I think, mainly because Shoucheng, who, along with collaborators, including Murakami, we may hear more about this thread in the next talk, I'm not sure, published a similar paper slightly earlier, but he always drew attention to our work on this. Okay. So as I said, I'm going to talk about the 3 papers I wrote together with Xu Chang, all in the middle 1990s, published in 3 successive years in Physical Review B. And it concerns electron-electron interactions in bilayer 2-dimensional electron systems. And one of the interesting things about bilayer 2-dimensional electron systems, where electrons are confined to 2 layers with a big tunnel barrier in between so that the number of electrons in each layer is conserved separately, is that even though there are no single particle processes that connect the layers, phase coherence between the 2 layers, this electron hole creation amplitude, where T and B stand for top layer and bottom layer, can be spontaneously non-zero. And this type of state we call an exciton condensate, actually a spatially direct exciton condensate, since the electrons and the holes are in different layers. And until recently, the only types of systems where this type of broken symmetry was observed occurred in the quantum Hall effect. I'll mention a little bit later that in graphene 2-dimensional electron systems, we're now starting to see, and in transition metal dichalcogenide 2-dimensional electron systems, we're starting to see spatially indirect exciton condensates without a magnetic field. But in this early work, what we were thinking of is systems in a magnetic field in which Landau quantization completely quantizes the kinetic energy. And it turns out that this broken symmetry state occurs when the sum of the densities of the top layer and the bottom layer is enough to produce a so-called filling factor 1, which means 1 electron for every state in the low energy band, which is doubly degenerate because of the presence of 2 layers. And, or another way to think of it is if you do a particle hole transformation for 1 layers, this is really a condensate of bosons, and the bosons are formed from an electron in 1 layer and a hole in another layer. And so in our work on this, one of the things that I learned from Xu Chang, or that he pointed out, is that because the order parameter in this system is a complex number and wants to have equal amplitude in the 2 layers, wants to be half in 1 layer and half in the other layer. If you represent the broken symmetry state by the layer state of the electrons in these systems, then if you have a block sphere where spin up is in 1 layer and spin down is in the other layer, then the vortices of this ordered state, which has a complex order parameter like a superconductor, the vortices actually are just objects where the system becomes strongly polarized to 1 layer or the other layer in a vortex. And so these are just exactly half of the skyrmions that Stuart was talking about in the last talk. They're half skyrmions here because the system wants to be not along some easy direction over much of the volume as it would in a ferromagnet, but it wants to instead to be half in 1 layer and half in the other layer, and it doesn't care too much what the phase relationship is. And so skyrmions have arisen many times. They had arisen in quantum Hall effects through the work of Shivaji Sandhi, Steve Kivelson, and others several years before this work. And one of the interesting about these topological order parameter textures in the quantum Hall effect is that the fact that Landau levels degeneracy is proportional of magnetic field, through what would be called the topological Hall effect in the context of spintronics, it actually turns out that these objects carry electrical charge. And that makes them much more interesting, much more accessible in some ways, because all you have to do to introduce a whole bunch of these topological objects into your system is change the Landau level degeneracy, so the system is forced to introduce a lot of charged quasiparticles. And, so one of the interesting things now, this work was, an early part of this work was done mainly in a series of beautiful experiments, mainly by Klaus von Klitzing and Jim Eisenstein in semiconductor quantum wells. But now there's a new generation of experiments in graphene bilayers, and it turns out that in those systems they're more homogeneous and it's much more easy to actually study the properties of these objects. And as I mentioned, so these spatially indirect exciton condensates are really electron hole boson superfluids, and for the first time you actually really can measure these systems because you have two layers and because you can make separate electrical contacts to the two layers. So this is one of the interesting types of experiments you can do. You have this bilayer two-dimensional electron system. You have broken symmetry, which turns out reasonably described by mean field theory, and like in a superconductor, there's an energy gap. So if you have this circuit and you don't have this shunt wire at the bottom and you try to force current through from source to drain, no current will flow at low temperature because there's a charge gap. But if you short the bottom layer to allow a circuit to flow, like electrons to flow around like this, then it turns out that there's lots of current at low bias voltages, and so evidently the current is carried by launching these bosonic electron hole pairs that move through these systems without any measurable resistance at this point. Okay, so let me switch to graphene. Very quickly, one of the interesting things about the graphene two-dimensional electron system is the honeycomb lattice. There's an A sublattice and a B sublattice, and that means the block states for every momentum are some linear combination of a component on one sublattice and a component on the other sublattice. And it turns out that at low energies, the states near the Fermi level, there are two states, different linear combinations of the two sublattices, and they're described by a 2D Dirac model, and they exist near one of these two inequivalent Brouin-Zone momenta. And what that means is that the electrons have a sublattice dependence that would make them two-component spinors, but they also have a valley dependence, which makes them four-component spinors. And so the quasiparticles in this system are four-component spinors. The case of two layers of graphene, I'll come back to a little bit later, but the main thing I want to emphasize here, which you can understand intuitively, is that the electronic structure of two layers of graphene depends qualitatively on how the two layers are stacked. So in this is the thermodynamically stable stacking arrangement, where one half of the electrons of one layer are adjacent to one on another layer, and these states are chemical bond is formed, which pushes them away from the Fermi level. And so that's a characteristic property of AB bilayers, and if you have AA bilayers, the electronic structure is completely different. So I said that these states that I worked on together with Shoucheng many years ago are formed in the quantum Hall regime. They're formed when bands are filled, when the number of electrons per Landau band is equal to an integer. And there's a generalization of that to these graphene systems, for example. This is, for example, from a recent paper on bilayer graphene. It's just a resistance map on top. This is from the group of Corey Dean at Columbia. And this is a stylized version of the data on top, on the bottom. And you can summarize it briefly by, the main thing I want to point out is that at all of the integer filling factors, there's an energy gap. So all of these gap states are some kind of broken symmetry state, and they're generalizations of these states with spontaneous interlayer coherence that occur when a bilayer system has only one of its two bands filled. In the case of bilayer graphene, you not only have valley and sublattice within each layer and a spin degree of freedom, but it turns out that there are two different orbitals that are degenerate within this Landau level, and you can sort out these states and by these resistance maps. And the interesting thing is that at nearly every integer filling factor, the system becomes strongly resistive, which is you wouldn't expect on the basis of interactions. And just to give you one example, this is the example of filling factor 0 in, this is actually single layer graphene. And so it turns out that in the first approximation for these systems, you have spin and valley degrees of freedom, and the interactions are independent of spin and valley. So the Hamiltonian is invariant under transformations in this four-dimensional spin-valley space. It's SU4 invariant. And you can, but it's not really exactly true that the interactions are independent of which valley the electrons are in. And this phase diagram up here is copied from the work of Kurotanov, in which there are two parameters. Turns out this valley dependence of the interactions is small, we know, and partly because it's small, it's difficult to estimate quantitatively, but you can parameterize it in terms of two parameters. This is sort of exchanging electrons between the two valleys, and this is a difference between scattering of two electrons in the same valley and different valleys. And what this shows is that somewhere in this parameter space, at a general point in this parameter space, the system is spin invariant, and it still conserves, the interactions still conserve the number of electrons in each valley. But along this particular line, there's a larger symmetry. And what's shown in the plot here are just exact diagonalization energies on a sphere as a function of angle of this parameter. And what they show is something we discovered by accident numerically, and that's along this line, the system has a larger symmetry. It has the SO5 symmetry. And somehow, maybe it's not surprising that this occurs at a boundary between an antiferromagnet and a Kekule. So all of this symmetry along this line is very close to the approximate symmetry that Shoucheng studied as a possible model of high-temperature superconductivity. And the quasi-particles in this system are four-component spinners, just like we learned about this morning, was a part of Shoucheng's way of thinking about these things. And so it may be that SO5 is related to some of these states in quantum Hall systems. I'll come back to that point in a minute. So, last part of my talk, I'm going to talk about a a new way of making Landau levels, a new way of making flat bands that in many ways behave like Landau levels, and in which some of the ideas that Xu Chang had taught me about quantum Hall effect physics might be relevant. So this is a picture many of you have probably seen before. It's two honeycomb lattices, one on top of another, so you can think of it as two graphenes, a red one and a blue one. And it shows the formation of Moiré patterns, which happens whenever you have regular two-dimensional patterns, periodic patterns, in this case honeycomb crystals, laid over each other with some small difference. In this case, it's just a difference of orientation. And you can see, both in this picture and mathematically, that's what's going on here, is that, let's say, if you rotate the red layer relative to the blue around some axis of rotation, then the displacement of the red layer depends on position. But for what you see with your eye, it's only the displacement modulo lattice constant that you see, or indeed that actually influences electronic properties. And that pattern is periodic, and the periodicity of that pattern, because d has to change by lattice constant for this to repeat, the periodicity is inversely related to the twist angle. So this is a system that's easily realized experimentally, and a number of experimental groups have worked very hard to have very good control over twist angles between two adjacent graphene layers. And this is a cartoon that from his paper by former postdoc Rafi Bistritzer, that I use to illustrate a way of thinking in a simple way, making a simple model of the electronic structure of such a system. And the idea is simply that you have tunneling between layers. The tunneling is sublattice dependent. The tunneling is strongly dependent on the local stacking between the two layers. And this is a picture constructed with one particular type of model. You can construct it in many other ways as well, including totally ab initio calculations, of one particular tunneling amplitude from one layer to another. It's a particular component of the sublattice dependent tunneling from, let's say, a B sublattice of the layer underneath to the A sublattice of the layer above. And it follows the spatial pattern that we know follows more or less from symmetry about how the sublattice-dependent tunneling depends on stacking. For example, at AA points where the two layers are right above each other, the electrons don't change sublattice when they tunnel from one layer to another. And so this off-diagonal tunneling amplitude goes to 0 at all those points. The tunneling amplitude is, of course, a complex number indicated here by a magnitude and direction of a vector. So the main point of this is that this tunneling amplitude is some function of position. The layers are actually far apart in these van der Waals structure. So the tunneling amplitude actually varies slowly in position. And you can think that you can approximate this sublattice-dependent tunneling by the lowest, approximately at least by the lowest harmonic in a sublattice dependent. So that's the approach taken in this paper. This is a bunch of different estimates of how the tunneling depends on wave vector transfer and momentum space. And it turns out the lowest possible wave vector you can have is actually the momentum at the Brouin zone corner itself. And the next one after that involves adding a reciprocal lattice vector. And that changes the value of this parameter from something of order hundreds of MeV to something of order a few MeV. So you have a very simple one-parameter model of this Moiré, of the electronic structure of this Moiré superlattice. And one of the things that was known when people study this is that when, when you have a large twist angle, that means the Moiré pattern, period of the Moiré pattern is short, the stacking arrangement is changing quickly, then when you go from one layer to another, the momentum changes by a lot, just by Heisenberg uncertainty principle, and that changes the electron energy of the electrons that you tunnel to in the other layer is very different from where you started, and that means the layers are very weakly coupled at large twist angles, and you can practically not see the coupling. But when you go below twist angles of a few degrees, the layers start to get strongly coupled. And the amazing thing that happens is that at a non-zero twist angle, these states in the as a function of momentum associated with the Moiré pattern, which are being repelled by higher energy states towards zero in both the blue conduction band and red valence band towards zero, they reach zero at all momenta very nearly at the same twist angle. So you get a very flat band, much like a Landau level, with a spin and valley degeneracy, and also an orbital degree of freedom because there are two of these bands. So you might think time is up. Okay, this will be my last slide apparently. So you might think that this is a lot like a Landau level, and maybe it is. Maybe the insulating states are a little bit like the insulating states that occur in the quantum Hall regime, maybe like the insulating states that occur in cuprate superconductors. Certainly, superconductivity is seen all over the place at non-zero integer filling factors, just like in the quantum Hall effect. At every integer number of electrons per Moiré, people see insulating states, and so maybe one of these, maybe this is this kind of superconductivity is described by some SO5-like theory, that there's some underlying symmetry to the system that applies across this entire region, which would be a very beautiful thing. So thanks for your attention, and let me just end there. Whoops. Okay.
Question or comment?
David?
So at the end of your talk, you were talking about states sort of analogous to integer quantum Hall states and about symmetries there. Earlier in your talk, you talked about fractional quantum Hall. Is there reason to expect or not to expect that fractional quantum Hall should become important in these Moiré systems?
In other words, gap states at fractional filling factors.
Yes.
There's no evidence for it experimentally yet. Maybe it doesn't happen. But I can say one thing, and you can talk also to Oscar Vafik about this, that it's clear that the interactions within the electrons within these flat bands are very strongly interacting, and the states at non-integer filling factors are totally reorganized by electron-electron interactions. At integer filling factors, it might be that that there's a broken symmetry state around which the quantum fluctuations are not extremely large, and so nobody's seen any gaps at fractional filling factors, so that's a disappointment. But one of the things that's interesting, this is just from a calculation from the point of view that we're, in my group, applying to the system, and the point it makes by looking is the phase diagram of the flat band states as a function of twist angle and interaction strength. And there are black regions and yellow regions, and all that says is that some of these systems have a quantized anomalous Hall effect, as you, for example, may be seeing experimentally, and some do not. And those that do have a fractional quantum Hall effect they indeed might have these kinds of charged textures in some kind of order parameter that are actually the lowest energy excitations, as happens in the quantum Hall effect. So there's a clever title of a paper I always remembered, disallowed by the editors by Shivaji Santi, in connection of fractional or quantum Hall effect with the spin degree of freedom, and he said nu equal 1 is a fraction 2, and by which he meant there are non-trivial interactions at fractional filling factors, so at least that part of fractional physics I think has a good chance to happen here.
Question?
Yeah.
Allan, can you comment on the role of electron-phonon interaction and whether we're in the regime of high-frequency phonons, or we have low-frequency phonons which sort of just move layers relative to each other?
So I didn't mention phonons. There are low-frequency phonons. Andre, for example, as you may have noticed, has done some work on possible role of low-frequency phonons in this system. But one thing that's a little bit different, of course, is that there are high-frequency phonons that have energies that are very much bigger than the electronic bandwidth. And that means that there are phonon-mediated interactions between electrons that are also essentially instantaneous, like Coulomb interactions, and they certainly must play some role. Yeah. But very soft phonons that have an energy small, even compared to electronic bandwidth, might also be playing a role. So I didn't have a chance at the end to say, too much about where we are in understanding this. Maybe that's a good, because maybe we don't understand too much for sure yet. But I'm very confident with all of the experiments that are going on, all the theory activity, that that understanding will improve.
So I would like to ask a materials question.
Sure.
So graphene has a very special band structure, and now people are twisting all kinds of materials which have small gaps or which are more on the wild side. So is there any limitation, or can we twist now everything which is 2D and looking for surprises? Or do you have an idea of what comes out?
Yeah. So I do think it is interesting to twist things. What happens in more conventional materials like two-dimensional semiconductors when you twist them and get long-period moires is the bands just get flatter and flatter as you approach zero twist angle and go to longer and longer period moires. And and that's just because the electrons get trapped somewhere in a periodic potential, and the lattice constants effective lattice constants getting bigger and bigger. So it can be interesting, all of these systems, but the graphene system seems to be unique in that flat bands occur at what is actually a convenient finite angle. That means puts much less stringent on the perfection of the materials to let this kind of physics be revealed. And there's a very nice paper by Ashwin Vishwanath and collaborators that you might be aware of, that and various other things strongly suggest that the actual flat band at this finite twist angle is related to the Dirac Hamiltonians of the individual system. So as far as I know, that was something that's only going to happen in Dirac systems.
Okay, since the time's up, let's thank Anna again.